Okay, so you must have seen this sequence in one form or the other, or you will see it once you do your hands-on on Thursday. This is usually what a sequence is represented as. What format is this? It's called fast A. Okay, it's not fast A. It's fast A, and we'll see what it is called. Why is it called fast A in just a bit. So the top line, of course, is just an identifier. The first thing is an ID followed by some sequences or some numbers, followed by Homo sapiens, which is humans, followed by hemoglobin subunit beta, HBB. You had seen a version of this gene at some point, and then it says it's a ref-seq gene. So we will see this as we go along the class. Like this, you will keep seeing versions of this, but very broadly, you have an ID followed by some descriptive, right? So the first line here is called a description followed by sequences. This is called FASTA and says not FASTA or like pasta. Invented in 1985. There was actually a program which was used for designing the sequences and doing large-scale sequencing search. It was called FASTA, not FastSA. This was also called FASTA. So it actually stands for fast alignment, and that's why it is called FASTA and not FASTA. The idea was you have a description, you have a sequence. Usually the sequences that you will see will be 80 characters long because that's how much will fit in your standard screen in most cases, but there is no limit. So it reads from, so if this is your identifier, you read from here and this and so on. Right? And the entire length of this will be the length of the sequence that you are cataloging. In this case, for example, whatever is the length of that sequence will be the length of the gene. The reason we are studying this is because we started with this premise that given such two different sequences, so given a sequence which is ID1, which is AA, TA, maybe ID1, ID2, A, T, A, and ID3, which is, we are looking for a very hypothetical problem of being able to tell them apart in a very simplistic fashion. And what we approached was, can we do frequency statistics here to tell whether one is different from the other? To do that, we're going to use this idea of what is a random variable. We started to discuss about what a random variable is. And while you can read the definition on board, it's very likely that at some point you're going to forget it. So let's just try to see how does that look like. This class is okay. So the idea behind a random variable is, first, there is a set of sample space S. What is a sample space? A sample space is all sorts of possibilities that can happen in an experiment. The simplest experiment this is usually motivated by is if you're tossing a coin, there are only two possibilities, heads and tails, right? So we've seen this is a sample space for a one coin toss, because if I toss a coin, these are the only two possibilities that I can get. Similarly, for a sequencing experiment, what will be the sample space? Yeah, those are the only four possible spaces that we ever see in a sequencing experiment. Now, what a random variable does is it's a mapping from this sample space onto the real number line. So it will take these values and it will come up with a function, some function or some variable, which we're going to call the random variable, such that these possibilities can be mapped onto a real number line. So the one way, for example, this is done is, what is the simplest random number and random variable that you can think of in a coin toss setting? How will you map it, this sample space, to a real number? how will you do it? It's a random variable.
0 for head and 1.
Yeah, you can give it some arbitrary mapping, for example, right? You can give it a mapping that heads is 0 and tails is 1. Okay. You can design a complex experiment by saying that I toss it like 5 times. If I toss it 5 times, what will be an example of a random variable? So if I'm tossing it 5 times, so if I'm taking taking a coin and tossing it 5 times, one possibility is I get something like this or maybe this. What is the random variable here?
Number of heads.
Yeah, exactly. Number of heads. Very good, right? So if I just plot the number of heads, I should be able to see that becomes a random variable. While these are all possibilities that you can observe, this is your sample space. What does the sample space look like for this experiment? How large is the sample space? Correct. So 2 to the power 5. Right? I can get any possibility at each such location, and each of them is independent. And we will see what independence means in just a bit. This is my sample size. This is, so if I have to expand, I will have to write down all such possible combinations. That becomes my sample space, followed by the random variable, which is, for example, either the number of heads or the number of tails. Okay. So very similar, we can define in the sequencing experiment what a random variable is, and we will see this. If we start from a sequence perspective, right? So there are 2 categories of random variable. One is called a discrete random variable, which, as the name says, takes discrete values. A discrete value is something which is categorical in some definition. So, in this case, for example, this is one such value, this is one such value, and this is an example of a discrete random variable, right? So when I say this, what I mean is the set of possibilities where this is going to map. Those are discrete values, because either it will be 0 or 1. In this case also it's 0, because I can get either 1 heads, 2 heads, 3 heads, 4 heads, or 5 heads. I will never get 1.1 heads. So this is an example of a discrete random variable. Similarly, continuous random variable is something which will allow you to go from the space of possibilities that you have onto a real number line where the values can be anything in general. What will be an example of a continuous random variable that you can think of? Yeah, very simple, right? Like height. So if I take the set of distribution of heights in this class, some people will be 5.1, some will be 5.2, 5.3, and on the y-axis here, I can just plot number or frequency, and that becomes your random variable. Okay? So from a sample space, the sample space in this case is, what is the sample space in this case? Height, right? So height can go from what to what? It can be 0, it can be 0.001. We have not defined whether it's human or not. So in principle, it could go to infinity. Sample space, random variable. So sample space maps to a real number line, which becomes a random variable. And in this case, this line is continuous. That means it's a continuous random variable. Okay. Nothing to remember. Very easy to understand, right? Everything so far all clear? Okay. If this is clear, we can talk about probability distributions. So the idea behind probability is extremely simple, extremely intuitive. Broadly, it's inherently the way we understand this is chance, right? So if we focus only on the discrete random variable, if we design an experiment such that you're taking values from this set, which is x1 up to xj, we can assign a variable. Right now we're going to call it pj, which is the probability of observing the jth value in this set. Then pj is called the probability mass distribution function as long as it satisfies 2 criteria. Right? So the first criteria, if it is a discrete realization and if it takes only these j values, right? So this is an example where it can only take, your sample space is limited by these j values. So in this case, j was 2, in this case, j was 4, and so on. So if I do just one coin, one toss, either the probability of observing heads, the probability of observing the heads plus probability of observing tails is going to be 1, right? Because this is what my sample space is. So either I get a heads or I get a tails. So of course they have to add up to 1. The other possibility, the other property that it has to satisfy is the individual probability will be a non-negative value, right? Very, very simple to understand. The last thing that you're seeing, which is the summation value, which is equal to 1, is called a very simple thing, which is called law of total probability, right? So the probability of observing all the events given in a sample space, where you can observe j discrete values, is going to sum up to 1. Okay, is the definition clear? Law of total probability clear? Simply, given a sample space in a discrete world, the probability of observing each of them should sum up to 1. Right? Straightforward to understand. Okay, any questions about this part? Okay, then we're going to have a DNA sequence, let's say, where there are n bases. These n bases are represented as B1, B2 up to Bn. We can denote the probability of observing B1 to be A as P of A, because we are assuming that it comes from, inherently it is generated by a process where this species has some inherent properties of generating an A sequence. Similarly, we can denote PB1 as this should be, actually there's a mistake there. So this should be P B1 is equal to A is equal to P of A, P B1 is equal to C if P of C, and so on. Okay? Okay. Now the question that we are interested in asking is a very simple question. You can assume that this length n can be anything. At this point, it doesn't matter what is the length n. Given this notation that I have shown you, that if something occurs at a particular base, we can just substitute it to be the overall frequency of A, which is P of A. So even P B2 being A is P of A. In other words, the positions themselves are independent. So the chance of observing a particular base at a particular position is independent, and this is simply given by an overall frequency of A. Right? By law of total probability, we know that PA plus PC plus PT plus PG is equal to 1. The question that I'm asking is, if I give you a sequence which is n length long, so we'll define what is an expectation, but let me just put this in quotes. Just call it expectation. How many number of A's would you expect in this sequence, intuitively? We'll try to define what this word is. But broadly, what this word means is, on an average, given an n length sequence, how many A's do you expect to see? N by 4. Okay, so first answer is n by 4. What is the inherent assumption? So you have some intuition, right? Your mind is telling you that 4 number should arrive from somewhere. Okay, so first answer is n by 4. Any other answers? CA times n.
DA times
Okay, PA times n. Any other numbers?
DA times
A times n. Okay, any other? Okay, we'll see what the answer is and just discuss why such a simple, why such a question often arrives in biology a number of times. Okay, so I'll concoct a very difficult and a very non-standard way to solve this problem. One way to solve this problem is to, which we just discussed, is to think about what are the possibilities of things that can happen, right? In an ideal case, I can just keep enumerating all the possibilities that happen. So maybe, all A's followed by A, E, and I can count and it will never finish. I can do a very smart trick here, and I can say that, okay, let me focus on the question, which says that how many number of times do I see an A? For this, I can define at this point, the moment you see a number A, you can think about a definition of a random variable, right? So a random variable takes you from the sample space to a numeric value. How do I make it map into a numeric value? I can say that for any position I, if I observe this to be A, I will call my random variable xi to be 1 and this otherwise to be 0. Okay? So here I am defining, we should just say xi is 1 if I observe bi, which I can be any value from 1 to n, to be 1 if bi is equal to A and 0 otherwise. And by the time we come to the next class and we start to generalize this, it will become clear why are we taking this approach. Whenever you see a value which can only take 0 or 1, what kind of variable is it? You must have seen some version of this. Okay, binary. Okay, binary. Okay, any other names for binary? Binary.
sigmoid.
Sigmoid is a function which we can fit to this. Okay, or not. Okay, it's called Bernoulli, or Bernoulli. And we'll see how Bernoulli plays a role in a lot of processes that we're going to see and how you can generalize it to other processes. But is the argument clear? Okay, so I'm just defining one random variable. At this point, you said this intuitively, somehow this number came out. I'm trying to see like how do I actually, in principle, how can I calculate this? Okay, intuitively, what you're saying is maybe correct, may not be correct. But let's try to see in given a scenario and a counting process, how do we actually land up with that process? Okay, so if this is a random variable, what is the job? What is my job? My job is to calculate expected number of A. What is an expectation of a random variable? What is an expectation in general?
Number of times the value appears in a sequence.
Yeah, so expected, right? So my expectation of anything should be on an average, basically. Like what do I observe it to be seen? What do I observe that particular thing to be seen? Right? So before we start to go there, we will leave that particular thought there, and then you'll just describe a different set of terms. So far we have seen sample space. We know what is a random variable. One important thing is actually random variable is neither random nor a variable. Right? Why is it not random? Yeah, there is some realization to it, right? In the sense that you're actually taking a value, you're assigning a value to it. So it's not, it doesn't get assigned a random value. You know actually where those values are going to come from. And why is it not a variable? It's a function. It's a function essentially. Right? It's a function which maps one set of values to the other set of values. Right? So it's not truly random variable in that sense. The next concept is of, so we saw that, and the next concept that we're going to see is of independence. So if I want to define something to be independent, the simplest way to think about independence is as follows, that let's say if I have one event and if the second event is independent of it, it means that there is no information that is being transferred from the happening of event 1 to event 2. So if I now we're going to just define one way that event 1 happens and event 2 happens. If they are independent, which means that if this happens, nothing happens to this. If this does not happen, also nothing happens to this. Which means that if both have to happen and if both have to happen, then the first event should happen multiplied by, okay, nothing to memorize, just pure logic. Independent E1 and E2 are two independent events. If both events have to happen, then this event happens and the second event happens. Okay? That will only happen, if you are looking at this AND condition. So the way this is often denoted is if you are given, in this case I showed you only for two random variables, E1 or two random events in this case, you can generalize this to two random variables taking a certain value. The probability of observing x1 all the way to xn, take a certain value an. You can think of this comma as an AND operator, right? So this is an AND operator. This is simply because all of these n events are independent, you simply multiply them. Okay? That's basically what an independent event should satisfy. Okay, so far all clear? Okay, any questions about this? So at this point when I wrote E1 and E2, I did not say anything about what possible values can E1 take, right? So if I wanted, I could toss a coin and then I could sequence. Which means that the probability of getting a heads and getting an A is simply probability of getting heads. Okay. So I could, every time I toss a coin, I sequence one base or I measure one base, I could get whatever I want. I could also say that E2 is also another coin toss experiment. So in this case, these are independent events, but they are not identically distributed. I could distribute E1 and E2 to have the same distribution, in which case they become D. Independent and identically distributed. Okay, that's what that term shows here. Clear? Lot of terminology, but a very simple, very logical to follow. Any questions?
When both events are same, then we say IID.
Yes, if they are independent and they are identically distributed, right? So things could be independent, could be identically distributed. I could have 2 coins, but when I'm tossing the first, maybe I could stick the other one, in which case they're not going to be independent. Okay? So if I have, for example, these 2 coins and they are touched or they are joined by some hard, actually this looks like a spring, but they are joined by a hard thing here. If I toss it, technically this is 1, this is 2. They are going to have identical distributions because either it will take an edge or T, but they are not independent. Okay? Because the moment I get something here, I proxy because it's hard, we'll get the same value. Okay?
For identically distributed, what do you mean by it? Does the underlying distribution, let's say,
Yes, the underlying distribution is the same, right? So we'll see some other distribution and it will become clear what
even
distribution.
if the events are completely different, but the distribution, underlying distribution is same.
Very good and very deep question is what you're asking. Let me sort of explain that in a bit. So it's a very good question, right? So you're asking that, what is this distribution? Because I simplified this by saying that, I'm getting heads and everything is fine. But does it follow the same distribution? So distribution, as we will see, it can be is essentially a measure of, given the sample space, right? So for example, if this is heads and this is tails, if this is the sample space that you get from one coin toss in a 50% chance setting, this is the distribution that it would look like. 50% of the time you get this, and 50% of the time you get tails. So this, as we saw, is called a Bernoulli. Bernoulli distribution. Now this property that you assign to it is very, very important. In this case, both of these, when I was stitching them together, then both of them were Bernoulli distributions. That distribution that we assign to them, that has to be the same. Like it has to, that sample space in this case goes to only heads and tails. If I had maybe one more sort of different experiment where I'm actually bringing in a coin which has heads and tails along with maybe a die, or which is also called a dice, its sample space is right. So we will see what distribution this follows. It also can be collapsed into some formation of a Bernoulli, but this set of values that is going to take the distribution is inherently different, which means that they can be independent. I can remove this attachment. They can be independent, but they are not identical.
So the sample space should also be identical.
The sample space has to be identical if it is independent and identically distributed. It will taken from the same set of values.
So let's say in the case of the dice, we say if odd numbers come, then it's one case, and if the even numbers
You could do that. That's very okay. Very, very good. Right? Very, very good. So you could do that 1, 3, 5. They are heads, and the other ones are tails. Very, very good. You'll see how to convert from one distribution into another distribution. This is exactly what your computer does. So if you have ever simulated a random variable, for example, you want to simulate, a Gaussian, which we'll again will see, or a normal distribution. You can start from a random variable, which simply looks like this, which is what's called uniform distribution, and you can simulate a Gaussian distribution by following properties of how. Basically, the idea is that if I start from something like this, how do I make it in this formation? By restricting its sample space. Okay? And we'll see in a later class how is that done, but that's exactly what your computer does. So if you've ever simulated a random variable, if you generated this Gaussian curve or done any linear regression kind of setting, inherently it all starts from a uniform distribution and converts it into this form. Okay?
So then they won't be identical if we assume it this way.
No, when I do this definition, right? Once the moment I do this definition, and if, for example, in this case, this is pH and this is PP, and as long as I can ensure whatever is the pH is also the whatever pH you get here, which, for example, the simplest way to do is half and half, and everything here being 1/6, then it is identical. If I'm saying that this is what my sample space or observable space will be, even if I observe 1, the dice will tell you that just count it as heads. Right? Or in other words, you can make a die which has exactly, right? Could do that. Okay. Any questions? Okay, this is a lot of fun. You can think about all sorts of experiments that we do. Any other questions? Okay, now we'll formally define what is an expected value of a random variable. Very, very simple. It's simply the value that you observe multiplied by the probability that you're going to observe. Okay? It's in a sense what you call an average, right? So when we calculate the average of any quantity, when I take, for example, 1, 2, 3, 5, when I calculate average, I say that each of them is equivalently observable. So the probability of observing this is 1/4 times multiplied by this, right? So this is exactly that number here. it's very simple to see this in a discrete case. You can do the same thing in an experiment in the case of continuous value. But let's assume that you are given n different values, n different random variables. At this point, I don't know whether, so x1 is one random variable, x2 is another random variable, and xn is another random variable. At this point, we don't know whether they are independent or not. If I want to calculate the expectation of the sum of the random variables, x1 to xn, I can simply take this brackets out. So summation of expectation of the summation of random variables is equal to summation of the expectation of random variables. So for example, the two different random variables that we define in this case are, let's say, the coin and the dice. If I want to calculate on an average, what does that expectation look like after doing that simplification of making them both fall into the same sample space? I can take the expectation of what I get in terms of the die. So I said in this case, I could, let's assume that this is x1, this is x2, where it has, this one is x2. Simplest way to calculate the expectation if you toss them together would be, I could take the expectation of number of heads from here and the expectation of number of heads from this coin toss, and that will be the overall summation of the number of heads that I get from the joint. At this point, x1 and x2 don't even need to be independent, so they could, for example, be attached by a hard string. This property will still hold. Okay? So a reversal property in that sense. You could also think about a continuous random variable. In this class, actually, we will not take it, but I just wanted this to be clear because at some instances it does arise, and often that time the definition has to be redefined. But very simply, usually in the case of a continuous random variable, there's one very clear distinction. So if you recall, we define a continuous random variable which can take any continuous value in its sample space. Now because of that definition, so if there is a random variable which can take any value in from minus infinity to infinity, it's very hard to define what is the probability of observing a dot here. Right? A single point observation. The chance of observing something like this is extremely hard to define. Actually, the probability of that is 0. So the way this is defined is often by saying so one very clear distinction that you can remember, this is called probability mass function. This mass, essentially, the simplest way to remember is if you have discrete values, you can assign it a mass by giving it that those values are your mass, and this probability 1 by 4 is essentially what you will assign to weight. What we saw both in the case of discrete and random variable and continuous random variable is this is going to sum to 1. In the case of continuous, this is called a probability density function. Okay? And density, which is f of xi, is actually always measured between two values, right? So in this case, this area, don't have to remember anything, this area is essentially what you're trying to quantify. Okay? And by definition, this entire area of the problem where this is density will sum to 1. Okay? Is that clear? Here? Here? this is simply the sum over all possibilities of xi, which is this shaded area. Okay, this is what that denotes. We can also define expectation now with this definition for a continuous random variable. You can see that this is just the x fx. What is the value observed multiplied by the density that you observed. And similarly, for any given function of x, which is let's say g of x, you can define simply what you observe multiplied by the probability of observing this, right? So expectation is nothing but the summation of the value multiplied by its probability of observing. So 1 plus 2 plus 3 plus 4 plus 5 into 1 by 4. Okay. So the simplest, now this is all expectation. Now you would have also seen this term called variance, which in your other classes you would have defined as how much does my observation differ from my mean divided by some random multiplication of not n but n minus 1. Okay, we will not cover why that is n minus 1. We can actually do that in a much nicer fashion here. In the case of variance, so the variance of a random variable is how different is that random variable from its expected value. Okay. So this is expectation of how much does my random variable differ from the expected value of that random square. This is the definition of variance. So you will see, how does that get simplified. The simplest example of a random variable, which is called a simplest example of a continuous random variable, is the uniform random variable, which you see on the board. Okay, we'll see this in just a bit. More on the uniform distribution in just a bit. One more definition is the cumulative distribution function, which is essentially a measure of, given a particular value of x, how much area does it cover till I reach that value x. Right? So this is simply simplest to visualize on a continuous random variable function. So in this case, if I put my value x, the cumulative distribution function is till that point how much area have I covered. And by definition, if I go to infinity in this case, that value will be equal to 1. Right? Yeah.
What is the dependence on an expected value of random variable to its sample size? Or is it independent?
It is independent of sample size, right? So we'll go by definition. Whatever is the sample size, it could be infinite.
Right. But it will have probability to exist, a random variable, which will be a function of whether or rather if it's a discrete variable of the sample size.
Mm-hmm. Yeah, you will have to go through all the sample size, all the possibilities of that sample space.
So
some of them could have a probability of 0, right?
right.
It could, like for example, if I just needed, do a very random experiment where I say that the coin it can land up on your third, it can land up somewhere in between, which is h/t. But you have never ever observed it. So the probability that will get assigned to that is going to be 0. Okay. But the expectation will still can take that into account. Okay, because if you observe, for example, so let's just do that example in the case of we'll clarify, and that's what we're going to do next. So you said that coin toss is a Bernoulli random variable, right? It's Bernoulli because you observe only zeros or ones. So if I draw, either I will see this or I will see this. Now what does it mean to calculate an expectation? What is the Bernoulli? Is it will only take values from 1 or 0. Right? Random variable, the sample space is h comma t, which maps it to 1 or 0. I want to know what is the expectation of x. Why not? Okay, what is the definition? How do I calculate this?
Summation of x into its probability.
Okay, so 1 into
Plus b.
okay, does everyone see that? Expectation of a Bernoulli random variable is okay. How about variance? What does it mean? Half, what does it mean? Intuitively, all of you, like how should I understand? What does it mean? Like half is never observed actually. I never observe half. I only observe 0 and I only observe 1. How do I make sense of that half?
If you do it multiple times, then the expected value, like if you average it over, that will be.
Yeah, so if you do this experiment multiple, 100 times, and you tabulate the frequencies, you will see 50% of the time you will see zeros, 50% of the time you will see ones. Right? That's how you understand. What will be the expectation? What will be the meaning of variance of x? What does variance of x here mean? So by definition, it's a measure of how much does my random variable differ from my expectation. How will I calculate this? If you calculate this, it will become clear, how to go forward. How do I calculate the variance of this? So we'll just go by definition, right? So expectation of x is half. Okay, what do I do next? Simply, yeah, so I simply can substitute value, right? 1 minus half square. Definition of expectation. Now, what is your random variable?
X minus half.
X minus half square is kind of your random variable. Okay? So any function, right? So if x is a random variable, if I do x minus half, x minus 1 or some operation of, it is still going to map to the real number. Okay? So any operation f of x is also a random variable. Okay, it doesn't matter as long as this is a mathematical function, it will be a random variable. Right? A real function. Okay, so this is now your new random variable. Right? So 1 minus half square, definition of expectation of something is that value that I observe. So when I get 1 minus half square. What do I multiply this with? Half, right? Because the probability of observing 1 is half. What is remaining? 0 minus half. What is this equal to? 1 by 4. Expectation is half, variance is 1 by 4, right? What does it mean? Intuitively, what does it mean? Like in an experiment, what does it mean?
That is the maximum definition that can happen out of the variance variance.
Yeah, so if I do this experiment, on an average, I will get like, sometimes I'll get zeros and sometimes I'll get ones, but there will be some spread, right? If I quantify that spread, that how much is it differing from that, so if I do, for example, 5 experiments, sometimes I get 0, 4, so I get 1, 1, 0, 1. The amount of deviation that you are seeing this from half is something which is captured in that number. And variance in biology, this is very early on, variance in biology is usually a good thing. You want things to be variable that allows you to sort of capture what is going on. So in other words, variance is a measure of information, very broadly. If something is going to be very similar, right? Like, so everything was in biology, like the reason biology is hard is because things are changing. The reason because is cancer is hard to solve, for example, is because what one person gets is not what other person gets. So if I quantify this, I can quantify this in the form of variance. Now the variance that I see in terms of, let's say, mutations, which we will see in a few classes later, that's very, very high. And if that is very, very high, it becomes a hard but an interesting problem to solve. Okay? Okay. Talked about the cumulative distribution function already. For a given discrete case, this is even simpler. If I want to calculate the cumulative distribution function, it is for a particular value of x. If I just sum up what is the probability of observing x or below it, that is your cumulative distribution function. So simplest to think in terms of, for example, 1, 2, 3, 4, 5, 6. Let's say we did an experiment with 6 heads. If I want to calculate T of CDF at value of 3, it is the value of observing 1 or 2 or 3. Okay? It's essentially this area, which is written as x is this equal to 3 for any random variable, such as hyper. Okay. The important properties that it satisfies is, if you go to minus infinity, for a continuous case it's going to be 0, at plus infinity is going to be 1, because again all your area will be encompassed. And between any two values, a and b, it's given by simply, so if I have a, this is f of a. If I have b, this entire stuff is f of b. So if I subtract f of b, which is this, from f of a, I get the probability of the random variable lying between a and b. Okay, so what the final property shows. Okay, so we'll take the example of uniform again. So if f of x is 0, let's say a random variable is uniform between 0 and 1. If I take 0 and 1, it's uniform between 0 and 1, right? This means if I want to calculate, for example, what will be this equal to? So this is a and this is b. Yeah, this is f simply f. For a uniform random variable, the definition is probability that it is less than equal to the fact that it belongs it is uniform between two values is b minus a. Right? This is simply f b minus f of a is equal. Okay? This is the definition of uniform random variable, which you can see why that is the case. This value is b, this area, this is 1. So this area is a cross 1, this entire area is b cross 1, subtract it, and it will lie uniformly. Okay? Okay, I think it's a good stopping point. My idea was to cover more slides, but we'll move faster in the next slide. But hopefully the definition is clear, and we'll move faster from there. Once you come back, we will see how can you make the variance equation much more easier to understand, and why it collapses to that form, followed by doing an actual exercise where we go back to our original question, which we asked that on an average, how many number of A's will you see? Okay. But hopefully, you can actually now, if you can just give me 30 seconds, you can probably see why somebody said n times PA. Okay. So we started from this. We said it's a Bernoulli random variable. So if it is 1, if I get an A, and if not, it's 0. I asked for the expected number of A, okay, which is what assumption I'm going to make, which is also implicit, was these are independent and identically distributed, right? So if I see B1, I don't know what will happen to B2. I know that it can only take values A, C, T, and G. So it's identically distributed and it is independent. So by definition, if I want to calculate expectation of A's, how do I write this part in a format which will make it look like an expectation? Number of values, which is, let's say, number of A's. If I want to calculate here, what will it equal? If this is your random variable xi, what is the number of A's here in this sequence? Summation of xi. Okay. Number of A's in the sequence is simply summation of xi. Now, expectation applied on both sides. Okay. Expectation of sum is equal to sum of expectation. Expectation of a Bernoulli, right? We'll just write it as PA. We wrote it as for a Bernoulli with probability P. We'll see this in the next class. Expectation of X is just P. For example, in the case of heads, this is probability of observing heads. Whatever you are coding as 1. If I coded heads as 1, then this is simply the probability of heads. In this case, I coded this as 1, and I said that happens with the probability of PA. So this is N times PA. If this is not clear, we'll do this again in the next class. But this trick, if you understand, the rest of the stuff will become much more easier. Okay? This is called an indicator variable. If anything which is indicating the event that you want, that's called indicator variable. We'll come back and do this exercise again. Okay? Thank you.
What would be the distribution of PA?
PA is the probability itself.
Right.
PA is the probability of observing an A.
Right.
So initially I had said that given a particular organism, you can assume that A happens with the probability of a particular frequency. I had asked that if I told you that this is A is a frequency, and if I give you the length of a sequence n, it's kind of intuitive to think that the number of A's that you will get is the probability of A, because that's also the frequency, multiplied by the length of the sequence. Right? Here I have broken that same problem down in a slightly more mathematical fashion and showed that it is indeed n times E. Right? It will become clear when, right now we were dealing with one base, so it was very simple to understand. But if you recall from our last class, we had started to talk about enzymes which can cleave the DNA at random sites. These are called endonucleases or exonucleases. Sometimes they look for sequences which look like ATA, ATA. So if I give you an enzyme and you want to do recombinant biology with it, what is the expected number of cuts that you can make in your DNA? In which case, this is a much lengthier sequence. So we'll come back and calculate those statistics. Okay? Any other questions? Okay, thank you.